Okay, hello. So welcome to Module 3, which is all about Gauss's law. So I've divided this up into two videos. In the first video, I'm going to just explain what Gauss's law is, the math behind it, and why it's useful in electricity and magnetism. It's basically a shortcut for finding the electric field. And then in the second video, I'm going to explain basically like how to use it. So like how you can exploit specific symmetries with charge distributions to find the electric field of like a complicated array of charges using Gauss's law. So like we'll go through a bunch of different specific examples, some of which I think will be very useful for your challenge this week. Okay. So Gauss's law is a fundamental principle in electricity and magnetism that basically relates the electric field that is going through a closed surface, which you now know, having done the tutorial last week, is called electric flux, to the net charge trapped within that surface. Okay, so like what it is here, let me just write sort of like a short form version of that. So like we're relating the electric flux. Remember, this is the symbol for electric flux. It allows us to relate the electric flux, which is the electric field, like basically how many electric field lines go through a surface, a closed surface. Okay, remember that's the definition of flux. Remember we defined it in the tutorial as the dot product between the electric field and the area vector. So it allows us to relate the electric flux to the net charge that is trapped within that surface that you're using for the flux. So it's basically like relating, it's like proportional to like the Q, like how much Q is enclosed within the closed surface. So like Q enclosed, that's Q, remember Q stands for charge. So how much charge is trapped within the closed surface? Okay, so that's Gauss's law. Okay, so let's look at a very like simple example just so you can kind of see how it works. So let's imagine that you have just like a positive Q and you want to know what the electric field is at this point here. Okay, some distance, we'll call this distance capital R away from the charge. Okay, I want to know what that what the field is at that spot. Okay, so we know what the electric field looks like from a positive charge. It just radiates out in all directions. Okay, you saw that last week. And you also saw the equation for electric field last week, right? It's just 1 over 4 pi epsilon naught times that charge, like the charge Q, divided by that distance squared. And it's in the direction of like r hat. So it's like it's in the direction, like if I were to draw the vector for the field here, it would just be in this direction here, r hat. Okay, at that point there that I'm interested in. So this is just a review of last week. Okay. So you also saw in the tutorial last week that the flux is defined as, remember, this is electric flux. Electric flux is defined as what we call the surface integral of the electric field times the area vector. Okay, this is just another way of writing like the dot product between the electric field and the area vector. And remember, the area vector is a vector that is perpendicular to the surface. Okay, and its magnitude is proportional to the size of the surface. Okay, that again, you saw that in the tutorial. Okay, so this is the definition for electric flux. If I were to substitute in like the electric field, so like using my example here, if I were to calculate, if I were to sort of like substitute in electric field here, I would get 1 over 4 pi epsilon naught q over r squared dA. Okay. And I mean, what does that dA refer to? It refers to some area, like for a surface that I draw around the field lines. Okay, so this dotted, let's say this dotted line is a spherical surface that I draw. And I've got my charge inside the surface. Okay, and I draw this the surface so that it is exactly at the point that I'm interested in finding the field for. So actually, let me draw it a little bit better. Let me draw it so that you can see it a little bit better. Okay. So this is R. This is capital R. That's where I'm interested in finding the field. These are the electric field lines. Okay, and I draw this Gaussian surface such that it intersects the point that I'm interested in finding the field. Okay, and then this dA refers to the surface area of that Gaussian surface. Okay, which is a sphere. I've made it into a sphere. We're going to talk about like why it's a sphere in the next video. But just imagine I draw some surface. It's an imaginary surface. And I basically draw it so that I can calculate the flux through it. Okay, and so what this dA represents in this context is the surface area of my, what we call Gaussian surface. Okay, so we're going to talk a lot about Gaussian surfaces, and Gaussian surfaces are just imaginary surfaces, like imaginary lines that we draw so that we can, and we draw them in such a way that the charges are enclosed inside them. They're closed surfaces, and we calculate, we use them specifically so that we can calculate the flux. Okay, so I've drawn a sphere. So this dA turns into, so if I rewrite this, 1 over 4 pi epsilon naught q over r squared. So dA, what's the surface area of a sphere? It's just 4 pi r squared. Okay, so that's the surface area of my Gaussian surface. Okay, and so now if I tidy this up, the 4 pi cancels with the 4 pi, the r squared cancels with the r squared, and what am I left with? I'm left with just the charge, Q, over the constant epsilon naught. Okay, and so that equals the flux. Okay, so now we've got sort of like two different expressions for flux. Okay, we've got this one that I just derived using the definition of electric field. And then I've got the one that I said that I mentioned before, where it's just the flux is the integral of the surface area of the electric field times that Gaussian surface area. Okay, and depending on how you manipulate the symmetries of that, like this is going to depend on the shape of the symmetry that you use for your Gaussian surface. Okay, we'll go over the different examples in a little bit. Okay, but you can basically make these two expressions for flux equal to each other, and that, my friends, is Gaussian is Gauss's law. Okay, so like Gauss's law is just the flux equals Q, and we say Q enclosed. So it's like how much charge is enclosed in the Gaussian surface divided by epsilon naught is equal to the surface area of E times dA. Okay, and this little circle just means surface integral. Okay, and this is Gauss's law. Gauss's law. Okay, so this is a really powerful thing because it allows us to find the electric field of like complicated configurations of charges without having to use complicated calculus. Okay, and again, by manipulating symmetries. Okay, so like if we assume if E, the E field, is parallel to the surface area vector, then this integral just becomes the electric field times the area. Okay, so like if the electric field is pointing in the same direction or opposite directions, but like parallel to the area vector of the surface that you draw, the Gaussian surface that you draw, then you don't even have to do the surface integral. It's just the electric field times the area. So this actually like neatens up, or like it simplifies down. Gauss's law simplifies down just to this, assuming this condition, like the electric field and the area vector being parallel. Okay, so like the whole name of the game with Gauss's law is to draw your Gaussian surface in such a way that this is true. And if this is true, then the equation simplifies to this, and then you can find the electric field of like a super complicated configuration of charges just by dividing the Q enclosed, like whatever quantity of Q you have enclosed in your Gaussian surface, divided by epsilon naught times the area. Okay, so this is like the way I think of this is it's a shortcut to finding the electric field at a given point away from like sort of like a complicated configuration of charges. Okay, and that's all it is. That's all it is. It's like, I mean, if you go back to sort of the definition of electric field and remember like what we did last week, the other way of finding electric fields is very complicated, right? It involves adding up all of the vector components of each individual charge that contribute to the field, or manipulating some sort of symmetry and setting up an integral, right? Which is what I showed you last week. But both of those are not easy, right? This little shortcut is much easier because all you need to know is the Q enclosed. You draw some surface, and we'll talk in the next video about like how to decide which surface to draw. But you draw some surface, and then you count up the charge inside that surface, and then you just divide by the area of the surface. Okay, so it's super easy to find the electric field, and the alternative to finding the electric field is very complex. So it's a very nice shortcut, and this works for any geometry. Okay, again, assuming the electric field and the area vector are parallel. Okay, which involves manipulating specific symmetries. Okay. This is one of the examples from the textbook. So this is just to get the idea across that the flux through any surface is just a function of how much charge you've got contained within that surface. Okay, so you can basically draw any closed surface and you can calculate the flux through that surface just by counting up the charges and then dividing by the constant epsilon naught. So let's maybe just do a couple of examples here. Like let's do maybe the simplest one and the most complex one. So like A and E, just so you can see how it works. Um, so so remember, like we've said that flux is equal to the Q enclosed of your surface, and like these like beige blobs that are sort of labeled S are the surfaces, the Gaussian surfaces. And they've been drawn, like with different shapes to make the point that the size and the shape of the Gaussian surface doesn't matter. What matters is how much charge you've got enclosed. Okay, so if we wanted to calculate the flux in situation A, we know that the Q enclosed in this Gaussian surface is just 2 microcoulombs, and then I just divide it by epsilon naught. So you can do that out. 2 times 10 to the negative 6 coulombs divided by 8.85 times 10 to the negative 12 barods per meter. And so that just equals 2.3 times 10 to the 5 Newton meter squared over coulombs. Okay. E, same deal. I count up all of the, so these outside charges don't matter. Okay, because any outside charge doesn't contribute to the flux. Because any line that goes into the surface, let's draw the field lines of this charge here. Any lines that go into the surface, like, are also going to come out. Okay, so like you can imagine that this one, is going to go. So there's not going to be any, there's no net flux contribution from these outside charges. Okay, it's only the inside charges that contribute to the flux. Okay, because like compare that situation to like these inside charges, they do have a net flux, right? Because these lines are going out and they're not coming back in. Okay, so what we do for part E is we just add up the net charge inside the Gaussian surface. So that's plus 6 plus 4 is plus 10 minus 10 is 0. So the Q enclosed is 0, so the flux is 0. Okay, because the net charge is 0. Okay, so that gives you hopefully an idea of what Gauss's law is. I will go over like many examples manipulating different symmetries in the next video.